Welcome to this lecture series in group theory. In this lecture, we will introduce dihedral groups and we will draw mainly from our previous discussion on the orthogonal group of the plane. So recall, what is the orthogonal group of any real inner product space? It is just the collection of those invertible linear endomorphisms on the vector space which preserve the inner product, and that can be expressed by this equation. So that's true for, or that's the definition for any real inner product space, and hence in particular for R2. But we also had an explicit description of that group in a later lecture, maybe. I don't know when exactly what was that. So we defined rotations via this cryptic looking thing, but the geometric idea was very simple. It is literally just rotation by theta. So those were the rotation maps, and it was easy to check that they are in the orthogonal group of the plane. And then we characterized rotations via this theorem that they are precisely the orthogonal maps or the elements of the orthogonal group which have determinant 1. Anything in the orthogonal group has determinant either +1 or -1. Those with the determinant 1 are precisely these maps. And similarly, we had the notion of reflection, and we had a similar characterization of reflections where this 1 would be replaced by -1. So those two things we had, and then I also mentioned another characterization of the orthogonal group, which was that the elements of the orthogonal group are precisely those invertible linear endomorphisms which preserve the unit circle. So this time the unit circle is being thought of as a subset of R2 rather than the complex plane, and this is how it is written. And the fact that the orthogonal group of R2 is precisely those invertible linear endomorphisms which preserve the unit circle is written over here. Okay. Some problems for practice. And now let us get started. Okay, so we want to discuss the dihedral groups. And what is the idea? The idea is the dihedral groups are symmetries of regular polygons. That is what we want to capture. So first we will define what are regular polygons for us, even though we know what they are, but we will define them in a very specific way. So the regular polygons for us would be subsets of unit circles, or the unit circle, not unit circles. So for us, the unit circle is a subset of the Cartesian plane, not the complex plane this time, just the Cartesian plane. So those points in R2 which are at a distance of 1 from the origin. So that's S1, and all of these circles that I've drawn here, they are just S1s. And what are the regular polygons? So the three-sided regular polygon is, well, you put a vertex at 1, 0, and then advanced by the correct angle. So if we want to describe the three-sided regular polygon, namely the equilateral triangle here, so the one vertex would be put at 1, 0, and then you advance by 2 pi by 3, right? This angle would be 2 pi by 3. Then you further advance by 2 pi by 3, and then you further advance by 2 pi by 3, you would come back. So that gives you a very nice symmetric structure. Similarly, if you want to draw a square or a four-sided regular polygon, you put one vertex at 1, 0, then you advance by 2 pi by 4, which is 90 degree, then another 2 pi by 4, another 2 pi by 4, and that's it. You get the 4 points. So this set of points would be our regular polygon. We won't be, taking into account these edges. Only the vertices is what we will record, and that would be enough, right? So for us, the n-sided regular polygon would be defined as a subset of the unit circle in the following fashion. It is just cos 2 pi by n, cos 2 pi k by n, comma sine 2 pi k by n, where k is going from 0 to n minus 1. So this should be now clear. I have already explained it using these pictures, what this set is. Okay, and the dihedral groups are precisely the symmetries of these polygons. So what do we even mean by that? What do we mean by symmetries of these polygons? That's a vague statement. So now we will get to the proper definition. Right. So suppose n is at least 3, then the nth dihedral group is defined as, those things in the orthogonal, or rather just those things in the general linear group of R2 which preserve the n-sided regular polygon. It's a very natural notion of symmetries. You might wonder, why have I taken linear? You can have alternate descriptions of the dihedral group, but I think this is a satisfactory one. Okay, so this is our definition of the dihedral group. If you consult some other texts, they may have defined it slightly differently. In some texts, they are defined completely abstractly, which I don't like. They are geometric objects and should be defined geometrically, and this is one geometric way of defining them. So now what we are going to do is show that the size of Dn is finite. That should be already clear, but we will show that in the course of the next few minutes. And further, we would write down all those elements. And before we do that, let's get a feel for it. So if n is 3, can we list out some elements of D3? Clearly, the identity map is there, of course. Rotation by 2 pi by 3 is there because it is just taking the vertex or permuting the vertices in a cyclic fashion. And similarly, the rotation by 240 degrees, 4 pi by 3, is also there. So these three rotations are present. Also, the reflection about this line is present because it is merely switching these two vertices and keeping this guy fixed. And similarly, the reflection about this line and that line are present. So we have listed out 6 elements of D3. Similarly, here we can list out 8 elements of D4. Rotation by 0 degree, rotation by 90, by 180, by 270. Reflection about this line, about this line, about this line, and about that line. So 4 rotations and 4 reflections, total 8 elements. And here also, you can list out 12 different elements. And it should already be intuitively obvious that these should be the only elements in Dn. N rotations and n reflections. And this is what we want to prove. So now let's get to it. So first we will show that Dn is actually contained in the orthogonal group. And in the course of the proof, we will have also shown that the elements of Dn, or each element of Dn, is either this rotation or this reflection. So S is the reflection about the x-axis. S is the reflection about the x-axis, and this is rotation by this particular angle. Right? So yeah. So let's try to show the first thing, and in the course of that, this will already be clear. And I'm not going to give a very detailed proof. I just want to give an intuitive proof. The details are an exercise. So here is how we will go about it. Fix some element of the dihedral group. We will show this. As we noticed in the recall and in the lecture corresponding to the recall, a general linear, an element of the general linear group lies in the orthogonal group of R2 if and only if it preserves the unit circle. Right? So that is enough for us to conclude that T lies in the orthogonal group of R2. So this is what we would like to now do. Okay. Now let's develop this notation. For each k in this set, 0 to n minus 1, we define this vertex vk as this element. So let me jot them down here for clarity. This is v0, this is v1, this is v2. Similarly, here you have v0, v1, v2, v3. And here we have v0 to v5. All right, so these are k vertices, the k vertices of the regular n-sided polygon. And now we will consider two cases. Case 1, the determinant of t is positive. Similarly, there will be another case where the determinant is negative. That will be an exercise. So say T of V naught is Vk for some k. And in the hexagon example, all we are saying is suppose V naught is, for concreteness, V2. Okay. So define or let T tilde be equal to this composite, right? We are just composing T by this rotation. Note that there's a minus sign here. So this is a rotation by this angle, but in the clockwise sense. And the reason this was done is to just have this equality. T tilde of V naught is V naught. Right? So T tilde of V naught is V naught, and T tilde is clearly in the dihedral group. One thing I didn't do is show that this is a group, but that is an exercise. The binary operation here is composition, and this is a group. So clearly this is an element of the dihedral group, Dn, and hence this composite is also in the dihedral group. So T tilde V naught is V naught, and the determinant of T tilde is also positive. Right? So it's a positive determinant element of the dihedral group which is fixing V naught. And our claim is, so we claim that T tilde is identity, and once we prove this claim, we would deduce that T is actually this rotation. Why? Because if T tilde is identity, then you can take this to this side by taking the inverse of this guy, and you would have this. And that would finish the proof essentially for this case. The other case is an exercise. All right, so to do this, we have a separate lemma, which I have very creatively named a lemma. And what does it say? It says that suppose n is at least 3 and T is in the corresponding dihedral group, such that it fixes V naught. So it fixes this particular guy, just like in the previous proof. So T tilde in the previous proof was fixing V naught. Here I have chosen T for simplicity of notation. So we claim that T is either identity depending on positivity of the determinant and is reflection about the x-axis if the determinant is negative. All right, so I hope the claim is, the lemma is clear. And using the lemma, the previous proof should also be immediately clear. Like you should be able to finish the previous proof once this lemma settles. So how do we do this? Assume determinant of T is positive, and the case when determinant is negative is an exercise. All right, and we want to show that T is identity, and for this we really want to show that, and hence we want to show that. And hence it is enough to show that T of V1 is equal to V1. Why is this enough? Because T already fixes V naught. If it also fixes V1, then it has to fix every point in the plane. V0 and V1 together span the entire plane. So this is all that we now need to do. So say T of V1 is written as a linear combination of V0 and V1, because any vector can be written as a linear combination of V0 and V1. So we do that, and now since determinant of T is positive, we have that B is positive. Right? Why is that? Because the matrix of T with respect to this ordered basis, V0, V1, is this, right? T fixes V0, so the first column is 1, 0, and the second column is AB, simply because of this equation. So the determinant is B, and therefore B is positive because the determinant is assumed to be positive. Okay, now we will make 3 cases. Case 1, B is greater than 1. And here is the main idea. T is in the dihedral group, so any power of T is also in the dihedral group. T, T square, T cube, everything is in the dihedral group. If you keep iterating by t in this equation, so keep applying t on both sides, this guy will keep blowing up. And at one point it will blow up so big that this thing cannot possibly lie in the unit circle. But since by definition the dihedral group preserves the regular polygon, the image of V1 under any element of the dihedral group should lie in particular in the unit circle. So that is basically what will give us a contradiction in this case. So let me write down the details and things will be clearer then. So we have TV1 is equal to AV0 plus BV1, which implies T square V1 is A0 V, sorry, what am I writing? AV0 plus BTV1. So what am I doing? I'm applying T on both sides. Just to be very, very clear, let me write that as TV0 because otherwise some confusion may be caused. So this is TV0. But what is TV0? TV0 is V0. And TV1 is equal to this. AV0 plus BV1, which is equal to A plus, some garbage times V0. That is not very relevant. Plus B square V1. That is the relevant part. So this, don't read too much into this. This is some garbage. So if you just keep iterating by t, you will see that t to the power capital N V1 is some garbage. Let me not write G, some A tilde times V0 plus B to the N V1. Right? For some A tilde. So that I'm not writing. A tilde is just some real number. But now, this we know lies in the unit circle. This is an element in the dihedral group. V1 is a vertex of the n-sided regular polygon. So this thing is also a vertex in the n-sided regular polygon, and hence in particular this lies in the unit circle. But this thing is equal to that, and if n is very large, if this capital N is very large, then this has very large magnitude because b is greater than 1. This grows without bound. So the magnitude of this cannot possibly remain equal to 1. No matter what you do, this magnitude will grow, and this point therefore is thrown out of the unit circle in particular. Actually, it is being thrown out of the polygon. That is really the argument, but whatever. So this thing cannot lie on the unit circle, and that's a contradiction. If capital N is large. So if capital N is large, then this thing has big norm, and hence this doesn't lie in the n-sided regular polygon, and that's a contradiction. Right, and similarly case 2, b is less than 1. So in that case, what would happen? This would become as small as you like. Right, so you can after some time ignore this. This will stop mattering. And then you'll have to worry a little bit more. Just think about it. So this case is an exercise. And the last case is that b is equal to 1. In this case, we have TV1 is equal to AV0 plus V1, which implies T square V1 is AV0 plus TV1, because T fixes V0, so I'm not writing TV0 this time. This is equal to that. But again, you use the definition of TV1 or the expression of TV1. This is going to give us this equation, which is 2A V0 plus V1. And therefore, in general, you would see that this is equal to N A V0 plus V1 for all n. Right, but then again, the same problem. This thing would become too big. If A is non-zero, then this becomes too big after some time, and hence this will fall out of the unit circle. So this shows that A necessarily has to be 0. Right, so A would have to be 0, and basically that's the point. Okay, I mean, that kind of thing you could have done here also. This is also growing. If A is positive, then this will keep growing, etc. Whatever, you can figure it out. But yeah, so this case was an exercise. It's a little work that you need to do, but these two cases I have done. And that shows that A must be 0, and that's it. Right? B is 1 and A is 0. So T fixes V1. So fill the details, whatever is remaining you can fill it up. So after this lemma, we are done. And that's what we said in the previous slide, that once we show that T tilde is identity, which we have done, we see this is the case, and hence that's it. That shows that elements of the dihedral group are either rotations of this sort or reflections of this sort. There are exactly two n things in the dihedral group. Just to summarize, if we write the reflection about the x-axis as s, small s, and the rotation by 2 pi by n as small r, we can write dn as this union. N rotations and n reflections. So this is dn, and hence size of dn is 2n. In many textbooks, dn, what we have called dn, is written as d2n, which is something that I don't like. Why unnecessarily confused? The nth dihedral group should be written as dn. Okay, and here are some simple observations. Order of R is n, order of S is 2. This is very simple. We know what is R, we know the explicit description of R, so the order of R is n and order of S is 2. S is not R to the k for any k, because the determinant of S is -1 while the determinant of this guy is 1. This is a very simple exercise where you use this fact. All I'm saying is, if this were an equality for some k and l in this range, then you cancel S from both sides and then you would contradict this equation. This is also just a matter of computation, so I can leave this as an exercise, but we saw the geometric meaning of it in the lecture on orthogonal groups, orthogonal group of R2. And this is just an extension of the previous one. So these are some observations. Here I've drawn some pictures to exhibit or to illustrate the reflections in question. So the 4 reflections for P4 are shown here, or the lines about which you reflect are shown here, and similarly for the hexagon. Okay, and yeah, I think I'll just star mark this one. This one is perhaps the most important. Yeah, these two things are basically the most important things that I wanted to highlight. Okay, using them you can compute anything that is written in the dihedral group. Suppose I write something like R S is SR square SR cube, and suppose we are working in P5. So then you can compute this using these two laws very quickly. Let me do that here. So we know that SR is RS inverse, or it's the opposite. RS is SR inverse, right? This one. RS is SR inverse, so I'll flip their positions at the cost of an inverse. This is SR inverse, but this S times S is 1. S has order 2, so this can be killed. And what we are left with is S times R to the power 4. So that's what it is. This complicated looking thing is just that. You rotate 4 times about, you rotate 4 times by angle 2 pi by 5, and then you reflect about the x-axis. That's what this complicated looking thing is. So it's very convenient. This description, all of this thing that we did, is very convenient to algebraically manipulate the symmetries of the n-sided regular polygon. Okay, so yeah, with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.